Hello, everyone. Wow, that was really loud. Welcome back to the Carneros Ballroom. How is day one of HashiConf treating everyone? That guy over there didn't clap, so someone should figure out why he's not having a good time. Great. We heard a number of talks today from HashiCorp engineers, HashiCorp customers, open source users about how they're using tools at scale, refactoring things, testing things. And tomorrow, we have just as an exciting schedule. That's English. We have one final closing keynote, but don't run away, because we have an amazing evening social, which I'll talk about more. So don't run away when Mathias is done. Stay right here, and I'll give you all of the details you need. You might have found a little thing sitting on your seat. I'll explain that in a little bit. But for now, I'm super excited to welcome Mathias, CEO of Travis CI, on stage to conclude today's keynote. Please give it up for Mathias.
Hi. Good evening, good afternoon. My name is Mathias. I am the CEO of Travis CI. I used to be an engineer at Travis CI, and as such, a couple of years ago, I developed a certain interest for the topic of complex systems, and specifically socio-technical systems, which is the intersection of automated systems and technology working together with humans, humans like all of you here. And as part of that, being an engineer, I had a very deep fascination with failure, and specifically because failure is something I can look at, failure is something I can fix. And just very recently, I've gotten a little bit more interested in the other side of that coin, in success. And when I talk about success, I don't talk about this kind of thing. It's like thinking about success is usually tied to thinking about, well, praise, or, I deserve this, I'm great at business. If you've seen The Big Short, you know what I'm talking about. So what I actually want to talk about is this kind of thing. There's a wonderfully flat line. It's an uptime graph. It's at 100% all the time. Yet we all know that underneath those hosted pages is something like this. Whatever system is keeping those pages up and running, probably, in a certain way looks like this. We don't actually know, because the cloud now is hiding a lot of that from us. But, the truth of the matter is that these things work, even with this being a reality that we still work in. And the flip side of that is that when we see a graph like this, the eye immediately jumps to that little dip in the graph. This is like the extended version of that graph I showed before. The eye immediately looks at, whoa, there's a dip. What happened there? No 100% uptime? We're obsessed with these kind of failures and also learning from them, which is great. Postmortems are a very common thing in our industry now, but there's a different truth about that graph. We have that little dip, but for the most part, everything looks good. And it turns out it's a lot harder to figure out why these things are actually working. And that's part of the purpose of my talk today. That's what I want to talk about. And so I want to start with a question for you. Who here is on call as part of their job? Okay, almost seems like a silly question at this kind of conference. First of all, thank you for keeping the internet running. And as a follow-up question, did anyone ever get a page to tell them this system is still running? Okay, I didn't think so. Because as the good person, Dr. Richard Cook said, nobody ever got a call in the middle of the night to let them know the system is still running. I mean, it would be nice to get a call in the middle of the night, but I'm pretty sure everyone who's on call actually values sleep. So what I want to talk about today is a theory that despite everything that happens, despite all of these failures that we experience, despite all of these pages that we're usually getting, our systems are working most of the time. And we're not spending enough time to figure out why that actually is. And as part of that, I want to look, as part of the theory behind complex systems and what we're doing as humans in it, in the socio-technical systems, I want to look at three points. One is complexity. The next one is risk. and the third one is adaptation. And I want to look at like a couple of stories for each of those, some from our industry, some from other industries. And these are all three different aspects that we're usually dealing with the software that we build today, especially here when we're building the future of infrastructure, which is, whether we like it or not, it's just going to get more and more complex. So I want to start with complexity. It's at the heart of everything we build. It's not a dirty word. Complexity is definitely a lot better than complicated to me. But it's definitely at the heart of everything we build, both in software and in organizations. And I want to look at an incident that happened in November 2007. It has little to do with software and technology, as you'll find. A truck in Texas, in the middle of Texas, was almost driverless, crossing a stop sign, and then crossing a parking lot. And at the end of that parking lot, it was crashing into a power station. And the truck driver was low on blood sugar, so he fainted. And that's why the driver was pretty much driverless. And it just turned out that this power station was powering a nearby data center. At the data center, everything worked as expected. The power source got switched over to a secondary source with a short clip in between where it was switched to backup power. And the cooling system also worked according to plan. Because of the loss of power, the momentary loss of power, it rebooted. And as it was designed for a 30-minute cycle for rebooting. And at the accident site, the rescue team arrived, and they were trying to figure out how do we get the driver out of the cab without electrocuting the driver and without electrocuting our team. So they talked to the utility company, and 15 minutes after the accident, the utility company shut off power in the region. So the cooling, I'm sure some people can see where this is going. In the data center, the cooling system started rebooting again. And so 15 minutes in, we're up for another 30-minute reboot cycle. And the data center and all the servers in it aren't designed for a reboot cycle that long. So things started getting heated up in the data center. And as a response, the hosting company who was operating there started shutting down servers. And that impacted quite a few large sites back in the day. 37 Signals was one of the companies who was affected by that shutdown. I'm curious, does anyone actually remember this incident? Wonderful. So I'm not going to talk about the hosting company's name because it doesn't actually matter that much. The unfortunate part about all of this is that there's no public documentation of this, except for news articles on the news pages that were affected by this outage. This is the only reference that you can still find. So all things considered, this was a black swan, an unknown, an event that was impossible to foresee. The black swan is a term coined by Nassim Taleb, and it's quite fitting for this. But that's not the part I want to focus on for today, because I want to look at the root causes real quick. If you look really deeply into the archived parts of the web, you'll find the paper trail of this incident. And initially, the hosting company said, well, the root cause was the utility company shut off power without warning, so we couldn't respond. And then over time, that root cause evolved into, well, it didn't have sufficient redundancy in the cooling system. So it's easy to point to cooling system because this is actually something the hosting company has control over. The hosting company doesn't have any control about a utility company, and let alone an emergency response team working, at a nearby accident site. So I want to just lose a quick word on root causes because this is like Sidney Decker, a very popular aviation person from aviation, basically said, root cause is where you stop looking any further. The cooling system is very convenient. It's definitely the component that failed. We can fix it. We installed more redundancy. So that's it. We're good. But the truth of the matter is, if you look at this incident, there was no single actor at fault. There was no single person that did something wrong. Nobody did anything wrong in this incident. Everyone worked as expected. But the thing is, all of the actors in this incident, they were not directly related. The data center people didn't know. They don't know the emergency response people. Or none of the three actors that we're looking at, they even worked in the same system. They were all just somewhat related. There was hidden coupling between the three of them that somewhat tied them together in a very unfortunate incident. All three of them were actually, showing normal behavior. They did what they always do. The EMT, the emergency medical technicians, they were working to get a person out of a cab. They were working to save a life, and probably multiple lives because they wanted to keep themselves from getting electrocuted. The utility company also didn't have any interest in losing a life because they would probably be held liable if that truck driver died because of electrocution. And the data center's cooling system it pretty much did what it was designed to do. When the people set out to design and build this data center, they designed it for a 30-minute reboot cycle, and that's exactly what it did. They didn't design it for power going off twice, but I mean, can't think of everything. I think the other solution that they could have gone for is add a third power source to the data center, but it maybe takes another component in this accident for that to trigger a similar kind of accident. So this concept of these people all exhibiting their own behavior is called local rationality. And that basically means, and this is from Eurocontrol, the European Agency for Air Safety, people do things that make sense to them given their goals, understanding of the situation, and focus of attention at that time. And if you look at all of these three actors in that incident, it makes a lot of sense. All of them did what they did. All of them did things that made sense to them at the time, given their goals, understanding of the situation, and focus of attention. They all had different focuses of attention. They all had different goals, but nobody knew about their respective goals and understandings of the situation. So, all of these actors worked as designed or as intended. So why do things go wrong? So I would extend this question into, did things even go wrong? That's what I actually want to leave you to think about today, but would be a very short end of the talk. So what happened in this scenario is that there were couplings between these actors that were not known to anyone. They were hidden. There is complexity that none of the actors was aware of, and that led to a situation that no one actually was able to foresee. No one who designs a data center thinks about a truck accident hitting a nearby transformation station. And so, while this has little to do with technology, we can learn a lot from that kind of scenario, because complex systems is all we build. It's like the future of infrastructure, as I mentioned before, is a complex system. It includes a lot of people, it includes a lot of technology, it includes a lot of automation. And the systems that we built, they keep growing and growing, and they keep getting more and more complex. And they keep getting more and more distributed. And they keep being tended to, they keep being run by and maintained by distributed teams, all forming a very, very complex systems together. And just very recently, we added one thing to the mix that increased the complexity in our systems even further: microservices. Microservices are great because they allow us to focus on a very small part of a big picture at any one time, but they come at a cost. But I want to look at Conway's law is it's very often quoted. But Conway's law says organizations which design systems are constrained to produce designs which are copies of the communication structures of these organizations. So if we apply that to microservices, we could say that microservices probably work very well with small teams that can work independent of each other. But if those teams don't work well together, our microservices won't either. If those teams don't talk to each other, how are the microservices supposed to talk to each other? So we need to make sure that these teams actually communicate well for the services to communicate well. And the other part of that is, this is a simple example of a microservices setup. As you can see, there's a couple of, bunch of couplings and connections between microservices, external services involved, and the quick summary of all of this is that none of these microservices that we build live in isolation. They're talking to other microservices, they're talking to the front end, they're talking to external services like here. It's the Stripe API, and it's Twilio, and it's SendGrid, and all of these little couplings, these interactions, can lead to very surprising behavior in production. And I'm pretty sure anyone who's run a certain set of microservices in production has seen these kinds of behaviors, because we're building a very, very complex system where where it's impossible to foresee any kind of behavior that might come up when these services work together. It's just impossible. If we have thousands of these services, we cannot possibly run through all of the permutations of interactions and potential behavior as a result of these interactions that's going to come out of a microservices setup. So, as much as I'm talking about the complexity of microservices, I actually think they're great. They give us the ability to iterate faster on smaller parts of our code base, but in return, we're buying increased complexity. Effectively, we make our systems more complex by splitting them up into smaller parts. And as a result of that, we have these surprising interactions between components that we design, but that we did never intend to. We have something called emergent behavior. These services talk to each other, they interact with each other, and because there are so many of them, there's so many permutations of behavior, there's behavior that's going to come up that's going to be surprising. And that's the crux for us to deal with systems now. It's to find ways to work with this emergent behavior and find ways to actually deal with it, to adapt to it. And thinking about microservices and Conway's law specifically, that there's a certain parallel between this data center incident and a microservices setup. There's independent actors, somewhat related but not really. There's a certain coupling between them. They're talking to each other but not really. And as a result, we're getting surprising behavior, unintended behavior. And I want to get back to that a little bit, to the truck accident. Specifically talking about the individual trade-off that everyone made. Going back to the three actors that we have, the EMT, the utility company, and the data center, all of them made trade-offs based on their circumstances. You can't really, if I were to ask anyone here after hearing this, you probably couldn't point the finger at a single actor in the system and say, well, this person or this component of the system is at fault. Not because. In that system, though, everyone surely could have taken their time to verify before they took the next steps. Utility company could have checked with the data center, assuming that the utility company actually knew that there's a data center attached to their power line. They could have checked with the data center if their system is going to be able to deal with another power outage. The data center could have been designed for a 50-minute reboot cycle of the cooling system, or the EMT could have tried to extract the driver with the power on, which is clearly not a great idea. But there's lots of possibilities that for all of these people to manage. There's lots of options for these people to work with. But in this case, human lives were at stake. So especially the utility company and the emergency response team did what made sense to them. The principle behind this is called the efficiency thoroughness trade-off, which basically the short summary for this is that demands for productivity tend to reduce thoroughness while demands for safety reduce efficiency. So it's always a balance between efficiency and thoroughness. If you look at any of these actors, they all had a certain balance that we were trying to strike. And the crux of this principle is that you can never be 100% efficient and 100% thorough at the same time. It's impossible. And this principle applies to individuals as well as organizations, because individuals are bound to the ITO principle, so are organizations. There's even a verb version that is sometimes used, in particular in this book, which I highly recommend because it is very much on point with this kind of topic. Success and failure as two sides of the same coin. And so in this data center incident, and even in microservices, and the systems that we build, who actually manages that complexity? We would, being engineers, we would love to automate that complexity away, but it turns out that by applying more automation, we build even more complex systems, so we just keep adding more complexity. Our systems don't manage themselves. They still need us in a certain way. So the part of the system that actually manages complexity is you. It's people. It's everyone who's sitting here, everyone who's working on infrastructure. And as you're doing that, you're always bound to risk. You're always bound to certain situations where you need to figure out what to do based on usually very little information. And for that part of complex systems, I'll look at a different industry, which is aviation. It's a very popular industry for that kind of purpose. So November '89, a British Airways 747 was landing in London Heathrow. It was very foggy, so foggy that the pilots couldn't actually see anything. So they had to do a Category 3 approach, which means that approach and landing is done with instruments only, with an autopilot. A couple of days earlier, the entire crew caught a stomach bug and got a prescription from a doctor that wasn't really approved by the airline, but was recommended by a doctor that was approved by the airline. So there's already a lot of stuff going on. In addition to that, the co-pilot was rather inexperienced, and he was actually not allowed to fly to do a Category 3 approach. So the pilot had to get a special permission from the airline, which they granted. It's not an unusual thing. It happens quite a few times, and they usually give that permission. And that is already an interesting set of circumstances, but there's more. As part of the approach, when the plane, during the flight, the plane was already was exposed to very heavy and unexpected headwinds, which cut deep into the fuel resources. They had very fuel left and had a high pressure to land in London Heathrow. They were, as part of the approach, they were diverted to a different runway, which meant the wind was changing, and the crew had to reshuffle procedures, checklists, and all of that to make sure that everything is still okay for that approach. They had tailwinds during landing, and effectively, because the air traffic controller gave them less runway, 10 miles instead of 12, they had a lot less time to lock in on the runway. And there's more. The approach lights weren't working. It's not really a big deal, when you're doing an instrument landing anyway, but most of the time it helps pilots, even in the last seconds, to figure out if they're actually, on target. Air traffic control withheld the landing clearance and pretty much until the very last minute, which was, made it unclear if the crew, in the end, was actually allowed to land. And last but not least, the autopilots didn't catch on to the runway's localizers, because the autopilots weren't actually built for this 747 model. It's like they're known to be a little bit of a hassle to get to work, and they're not always reliable. So effectively, the crew was now flying in an illegal approach. This was a situation that was not supposed to happen. There was a non-functioning autopilot, there was an inexperienced co-pilot who had a stomach bug, and the captain has been flying alone for the last 5 hours, which had everyone concerned. And so when the plane was finally trying to land, it wasn't aligned with the runway, as it didn't catch on to the localizers. And the captain pulled up the plane when it was already out of the airport's perimeter fence. The plane missed the hotel by 23 meters in height. That's 75 feet. And car alarms in the hotel's car park were set off, and fire sprinklers in the hotel were also went off. But the second attempt was successful. No one got hurt, no one died. The plane came out pretty okay. No scratches, nothing. And when they landed, in aviation, there's a thing called the mandatory occurrence report, which is basically a requirement. When you had a near miss or a certain set of circumstances came together, there's a long list, you have to file a mandatory occurrence report. When the pilot went to his locker, he found a note from the chief pilot saying, "Please come along with your crew. I want to talk about what happened." But he sent the crew home. He didn't talk to the chief pilot. He didn't talk to a safety inspector. He didn't file the mandatory occurrence report because he didn't actually think this was an unusual situation. After all, the plane landed. No one died. No one got hurt. Everyone arrived safe. The next day, the crew got suspended, and the pilot was trialed and convicted for endangering passengers. And he was demoted from captain, too. In an interview following that trial, another pilot said, "Endangering passengers is what they do every time they fly." So even other pilots said, well, this is not an unusual situation. So to the airline, this was gross negligence. The pilot clearly exposed all of the passengers to unnecessary risk and had to be put on trial. Just for reference, no one else was put on trial in this. The unfortunate end result of that was that 3 years later, the pilot committed suicide and became what's called the second victim of this incident. To the airline, it was gross negligence, but to the pilot and a lot of other pilots, this is normal behavior. This is the kind of risk that they usually deal with when you fly. And while the airline made the pilot a scapegoat, it should be pretty clear that there's a lot of other stuff going on. This is basically a summary of all the stuff that I mentioned before, but these are all contributing factors. There's a lot of normal behavior, a lot of normal risk that people, both the airline, air traffic controller, and the pilots usually deal with. There's a lot of production pressure involved in this, and yet it was a pilot who was convicted. Only the pilot, dealing with very normal circumstances. And that has me thinking a lot about our industry. We're kind of lucky, at least most of the time, that no lives are at stake. We're dealing with a different kind of risk. So last year I had the privilege of attending a learning lab at the Lund University, at the School of Human Factors and Safety Engineering. There were people from all kinds of industries were present, like air traffic controllers, pilots and pilot trainers. The pilot of this plane was not present, unfortunately. And there were people from shipping companies, and any resemblance of containers and shipping software is purely coincidental because these people were actually shipping containers. So as we had a lot of great conversations looking at how human factors resilience engineering came about, how it evolved from World War II to the 3 Mile Island incident, and how it's ever evolved since then. And all of these people, in the conversations I've had, asked me, "Why are you here?" When a plane crashes, it seems pretty clear, that it's terrible. People die, and when a container ship sinks, it's obviously also not a great situation. But what about a website? What happens if a website goes down? It's is it the same? And so my response to them was the outages and problems that we're dealing with, the kind of risk that we're dealing with, can impact 100 people, can impact thousands of people, or it can impact millions of people. Or in the case of the very popular social networks, it can impact 100 million people, or even more than that. And beyond that, the impact of outages is impossible to measure. We have this idea that to measure how much money we lost when a site went down, we're basically going to take the monthly revenue and cut it down to the 2 minutes that the site was down, and this is the money that we lost. And it's usually not the case. It's a very simplistic view. So those are very interesting conversations. And in our industry, we have this mantra of moving fast and breaking things, and that means we deploy a lot. But do we ever think about what is the impact of these deploys? What's the impact of rolling out a bug, say, on a healthcare site when there's a risk of exposing patient data? Or a social network that accidentally exposes private data about people that would make them victims in their own country? So we're getting back to, lives cannot be lost when you deploy software. There is a chance that it might. It's an interesting responsibility, which is definitely a topic for an entirely different talk. But we have these regulations, HIPAA is one example, but does anyone actually think they save us from introducing bugs that violate compliance? Okay, thank you. So as the last part of this talk, I want to talk about how we actually deal with this. How do we adapt? How do we adapt with the risks that we run into every time we deploy? So the deploy is what I actually want to talk about for a little bit, because the deploy is the single event that can actually introduce change in our system. And we've gotten to a point where single companies deploy hundreds, thousands, maybe millions of times, but I'm not actually sure if we're quite there yet. But every single one of these deploys is a responsibility. Every single one of these deploys is a gamble because it introduces a situation that has not existed before. It's a risk that we're taking. It's like the deploy button is actually more of, well, this could go either way. Not actually entirely sure, because we like to be very confident about it, and that's probably a good thing, but it's a risk. It's a very large risk by introducing a change into the system. We don't actually know what's going to happen. And there's an interesting model to outline that a little bit, and I want to talk about that real quick. This is Jens Rasmussen's dynamic safety model. So we're the little person in the middle. This could either be an individual, this could be a team, this could be an entire organization. And we have 3 boundaries that we work with. One is the financial boundary. This is a management pressure, pressuring us to be more efficient, to spend less money, and also the boundary of, well, an organization only has so much money that we can spend on something. The second boundary is workload, which means I can only work so many hours in a day before I crash, and I can only work so many days subsequently where I overwork before I burn out. And the third boundary is the safety boundary. In our world, once we cross that boundary, outages happen. And it's not just people that move within these boundaries, it's the software that we build that also moves in these boundaries. And so the problem the problem here is that both the workload boundary and the monetary boundary are very visible. We can figure out how much money we have, we can figure out how efficient management wants us to be, and we also know how many hours we can work in a day. But the safety boundary is one that needs to be explored. It's not really there. So it's more something, hold on, just getting back to this. This is the perfect equilibrium of where we're in a state but where we're equal in all 3 boundaries. There's not really a state to worry about. But the reality that we're working is more like this. We're actually fairly close to the safety boundary, because over time, every system that we build will actually push itself towards its own capacity limits, whether we actually like it or not. And in addition to, so the safety boundary is not visible. In addition to that, it's flexible. It changes. A system that existed 6 months ago is very different from a system that exists today, and therefore the boundary is also a different one. And if the boundary is invisible, how can we actually find out where the boundary is? The only way to find out where it is to actually cross it. And this is what we're doing every time we deploy something. Every time we're deploying something, we're pushing against this boundary. We're running the risk of actually crossing it. But we deploy another fix, and then we move back into the boundary, and we're safe. And so this is the interesting question. How do we, when we deploy so much, when we deploy so often, but the deploy is that event that regularly pushes us against the safety boundary, how do we actually handle that? How do we reduce the risk of moving across the boundary? And we found a fairly simple solution, which is we deploy small changes. Jez Humble likes to say, no change should live off master for longer than a day. And that effectively means, small changes should be going out to production, as soon as possible. And the assumption is that this will, be shipping small badges will reduce the risk of them actually doing a lot of harm, of them moving us across that boundary way too often. But the truth of the matter is we don't actually know. We don't actually know how often this happens because that boundary is so invisible, and we also don't have enough data that's widely available. There's little research that's being done on this, except for something like the State of DevOps survey, but we don't actually know what our ratio is of, well, this deploy worked, this deploy didn't work, and we actually have no data to work on to figure out, well, what are the conditions for why our systems usually work, and what are the conditions for when they fail? And the only source that we have right now in our industry is our public postmortems. And they usually only focus on, well, the stuff that broke. You rarely find a public postmortem that talks about, well, this is all the stuff that actually worked. And that's the interesting part to look at in an outage as well. You have all the stuff that failed, but all that other stuff. Think back to the graph I showed initially. There's a small dip in that graph is not really a terrible problem. It's not really a terrible thing when you also know and learn that all of your other stuff actually worked as intended. And what we also don't have is so-called thick data. This is the antidote to big data. Thick data is people's stories, people talking about their emotions, about their views of the world, about how they saw certain situations. Like as one example, all the information on that data center outage pretty much vanished. And how cool would it be to interview all of the actors in that system to get all of their stories? But we don't actually do that as an industry. As conversely, all that kind of data from the aviation industry is publicly available. If you look for the November Oscar incident, you will find plenty of documentation. And there's other industries who are great at that. As you know, these are two amazing books. The Challenger Launch Decision and Friendly Fire. One is, about the Challenger incident, and the other is about a friendly shoot-down over the Iraq no-fly zone. And these are hundreds of pages of accounts from people who are involved in this. And they outline a picture a picture of normal behavior in organizations that led to situations that, no one intended to happen, but they still happened. And they're really, really interesting accounts. There are lots of pages, but I think the Challenger Launch Decision is 600 pages, but the upside of that is that it's extracted from, I think, 2 warehouses full of documentation on the Challenger incident. And we need more stories like this for our industry. Because when we look at books like this, what we'll find is that success and failure aren't really 2 sides of the same coin. They're actually the same side of the same coin. Because things go wrong for the very same reasons that things go right. And that's a quote to think about that I'll leave you with for today. Thank you.